Hello everyone, welcome to the fourth lecture in topics in locally conformally Kähler geometry. So we were discussing last time about some cohomological constraints on the existence of LCK metrics on compact manifolds. So let's rediscuss this point. Homological constraints on compact LCK manifolds. And just as usual, we exclude the Kähler case. The first obstruction that we mentioned last time was that the Bott-Chern cohomology group of degree 1,1 is not zero. So if you don't know these cohomology groups, they are defined in the following way. They are the kernel of D intersected with the kernel of D bar. So PQ forms that are both D and D bar closed. Quotient to the image of DD bar. Okay, so let omega be an LCK metric with Lie form theta. Then, as we saw in the second lecture, when we discussed Weismann theorem, the one that stated the fact that on a compact complex manifold, Kähler metrics and genuinely LCK metrics cannot coexist. So as seen actually in the proof of that theorem, dj theta is a 1,1 form that is not allowed to be DD bar exact. So is not DD bar exact, right? Because we had some integration tricks that we performed in the proof of Weismann theorem. So dj theta is not equal to I DD bar of any f. So this means that its cohomology class in the Bott-Chern cohomology, it is a 1,1 form. dj theta is both D and D bar closed. And since it's not DD bar exact, its cohomology class is not zero. So therefore, H11 Bott-Chern cannot vanish. Okay, so this was easy to see. The other constraint was the fact that the first Betti number was strictly less than twice the Hodge number of degree 0,1. Okay, the first inequality is just common sense because the manifold is not globally conformally Kähler, right? We said from the beginning that we exclude manifolds that have Betti 1 equals to 0. It would be simply connected, and therefore any closed one form would be globally exact, and therefore any LCK would be GCK. So the point is, how do we get this second inequality? Well, in order to understand it, we look at the following inclusion of the first Durham cohomology group into the first cohomology group of the sheaf of holomorphic functions, of germs of holomorphic functions. Okay, remember that this group gives actually the Hodge number of B degree 0,1 via the Dolbeau isomorphism. So the complex dimension of H1 MO is H01 Dolbeau. Okay, we have this inclusion, right? And we have another natural map from our friend from the first point, H11 bot churn, to the second Durham cohomology group. This map is just taking the class of alpha, in the class of alpha, of course, in the cohomology that we consider. So it makes sense because alpha representative of a class in the bot churn cohomology is both D and D bar closed and therefore is D closed. So it is the representative of a cohomology class in the second Durham cohomology group. Okay, let's take as a fact, it is provable by writing down all the definitions and chasing diagrams, that the kernel of this natural map is actually isomorphic to the co-kernel of the first map. So to the quotient of H1MO and H1 Durham. Good. But who is an element in the kernel of F? In the kernel of F, we find a non-zero element, which is given exactly by the cohomology class of DJ theta, the bot churn cohomology class. Because we see that DJ theta is exact. So therefore, the class of DJ theta is mapped on the Durham cohomology class of DJ theta, which is 0, because DJ theta is also an exact two-form. So therefore, this kernel is non-zero. Therefore, this quotient is non-zero. This further implies that the real dimension of H1MO, which is twice the complex dimension, is strictly bigger than the first Betty number. Okay, so for compact LCK manifolds, number 1 and number 2 are basically the only cohomological restraints that we know so far. It would be very interesting to find some other cohomological obstructions. But since we discussed last time also compact Weismann manifolds, and they seem to be a very rigid subclass of LCK manifolds, they happen to have interesting cohomological obstructions. So let's treat the case of compact Weismann manifolds. So a very beautiful result of Tsukada from 1994 states the following thing. If MJ is a compact complex manifold admitting a Weismann metric, then two cohomological topological facts that are interesting happen. The first one is that the first Betty number is odd. And the second one is that the Hodge decomposition holds. When I say Hodge decomposition, I don't mean the Hodge decomposition that we used at some point in the proof of the fact that if theta is parallel, then the Morse-Novikov cohomology vanishes. There we use the Hodge decomposition that is always valid on a compact manifold. But here by Hodge decomposition, maybe I should put it in quotation marks and explain myself. I mean that the Betty numbers are the sum of the Hodge numbers whose B degree is such that P plus Q equals the degree of the Betty number. So this is what I will mean today by Hodge decomposition, without having any symmetry between the Hodge numbers. So this does not imply that HPQ is equal to HQP. Okay, if you are familiar with the spectral sequences, this equality between the Betty numbers and the Hodge numbers would be rephrased as the degeneration of the Fröhlicher spectral sequence at the first page. But we won't state it like this. Okay, beware that the first point, that the first Betty number is odd. So this happens on Weissman manifolds, because otherwise we have examples of LCK manifolds that are not Weissman, whose first Betty number is even. So small exclamation mark. So one is not satisfied for any LCK. If you remember last time, we even gave an example of an Olle-Klaus-Thoma manifold in complex dimension 3. That was of type S equals 2, T equals 1. And that had first Betty number equal to 2. So this is something very specific for Weissman. However, point 2, so far we don't have any example of an LCK, compact LCK manifold that does not satisfy the Hodge decomposition. So far, the known examples of LCK manifolds, of course, compact. We didn't even think of considering the non-compact case so far. So the known examples do satisfy Hodge decomposition. So it might be very tempting to formulate a little conjecture that maybe LCK enforces this relation between the Betty numbers and the Hodge numbers. Or just as interesting would be to provide a counterexample. Provide an explicit example of LCK without Hodge decomposition. In any case, our job today will be to try to prove Tsukadas theorem. And since it will be quite involved and it will heavily rely on many computations, at some point we will have to trust several facts that are not that difficult, but they should be read in, they should be done by hand actually. And they are also found in Tsukadas' paper. Okay, so the proof will be quite involved, but the proof introduces a very important object for Weissman manifolds, and that is the so-called canonical foliation. So we will use heavily that the metric dual of the Lie form theta and J of the metric dual are Killing vector fields I think we already discussed for the metric dual, but you can do it also for J of the metric dual. So killing vector fields meant that their flow preserved the metric. They are also holomorphic vector fields. So what do I mean by holomorphic vector fields? They are real vector fields, if you understand them. So theta sharp and j theta sharp are real vector fields, but they are holomorphic in the sense that their flow preserves the complex structure. So this is what we mean, what we intend by holomorphic vector fields. Okay, and finally, they commute. So the Lie bracket of theta sharp and j theta sharp is 0. So this means that the distribution generated by theta sharp and j theta sharp, so I would say that the distribution, so the assignment in any point of the manifold of the span of theta sharp and j theta sharp in that point. So this is an integrable distribution, since the Lie bracket of these two vector fields lands in the same space, being 0. And of course, it means that it defines a foliation. Defines a foliation F whose leaves are one-dimensional complex submanifolds. So of course, by foliation, we mean, so to any integrable distribution, we have an associated foliation. This is just a partition of the manifold into smaller submanifolds, and these submanifolds are the ones whose tangent bundle is given by the distribution. So in our case, the foliation given by theta sharp in j theta sharp is so called the canonical foliation of a Weissman manifold. This foliation will play a key role because it will allow many correlations between Weissman manifolds and Kähler geometry. So far, we said that we stay away from Kähler manifolds, but somehow with Weissman manifolds, we are getting very closer. So this correlation is done through this canonical foliation, and we will understand this fact. So to understand what we will discuss, I will just recall some basic facts about foliations. Some terminology that we will use. So I will call F, calligraphic F, the foliation. Then it has a short exact sequence. Given by the tangent bundle to F, which we denote by L, and the conormal bundle of F. We shall call any tensor field on this conormal bundle tensor field phi, let's call it, of the conormal bundle Q is called holonomy invariant if it satisfies the following property, that it is invariant, so the flow of any vector field tangent to F preserves this tensor field. So in other words, if the Lie derivative of phi along X is 0, where X is any vector field tangent to F. So of course, by tensor field, I mean, this is the general terminology, but in practice, we shall be interested only in metrics or complex structures. For this kind of objects, we will be interested in the holonomy invariance. Okay. Then we shall call this foliation a Riemannian foliation. If there exists a holonomy invariant metric G on the conormal bundle Q. So let's call it GQ. So as I said, we shall be interested in tensors that are holonomy invariant as being the metrics or the complex structures. So we shall see very soon. And finally, a metric on the manifold where we consider this whole thing is called bundle-like. If the induced metric on the conormal bundle is holonomy invariant. Is holonomy invariant. So by induced metric, I mean by identifying the metric orthogonal of L with Q. And therefore we have an induced metric on Q. Okay, this being said, we can state what the transversally Kähler foliation is. So a foliation F is transversally Kähler if, first of all, is a Riemannian foliation. Let's call GQ its metric, that is holonomy invariant. There exists a holonomy invariant almost complex structure JQ. Let's put the subscript Q for anything on Q. Course of the conormal bundle, with respect to which the holonomy invariant metric GQ is Hermitian. So G of JQS JQT is the metric for in SNT for any sections of the conormal bundle. Okay, so far nothing special, but the important condition is number 3, that requires this almost complex structure to be parallel with respect to the unique connection nabla prime, I will call it, that is metric and torsion free. Or associated to GQ. Okay, so this of course mimics what you already know, that there exists a unique connection that is metric and torsion free associated to a metric, and this is the Levi-Civita connection. So this is exactly the connection on the conormal bundle that we shall consider. And JQ is required to be parallel with respect to this unique connection. Okay, maybe I will put this as a remark, that there exists indeed a unique metric and torsion free connection nabla prime on the conormal bundle Q for a given Riemannian foliation with holonomy invariant metric GQ. One can explicitly write down this connection. So if you want to write down who is nabla prime of S, where S is a section of the conormal bundle, we distinguish two cases. We have to evaluate it along a vector field tangent to F or orthogonal to the foliation. So this is either the projection pi, so sorry to go back where we had the, yes, let's call this pi. The projection of the tangent bundle to Q. So it's either pi, the Lie bracket of X and YS, I will say immediately with this YS, when X is a section of L, or pi of the normal Levi-Civita connection of X and Y S when X is a section of the orthogonal to L. So where S is a section of the conormal bundle and YS is a vector field that projects to S. Okay, and this is the case when G is bundle-like. So we have already a metric on M, and the induced metric on Q is holonomy invariant. That's why I said here that we take the Levi-Civita connection. The Levi-Civita connection corresponding to G. Anyway, this might seem technical, but obviously things are not complicated. Okay, the true point here is that we have this proposition. The canonical foliation of a Weissman manifold is transversally Kähler. And this indeed will make the passage from Weissman manifolds to Kähler manifolds. Okay, let's prove this quite quickly. Let's prove the proposition. Of course, we are still in the body of the proof of Tsukada's theorem. So for the proof, we identify the orthogonal of L with Q. And this means that on Q, we can get for free an induced almost complex structure and the Hermitian metric. So we endow the conormal bundle with an almost complex structure JQ. And the Hermitian metric GQ. Okay, using the properties of theta being a parallel form, so of theta sharp and J theta sharp being killing and holomorphic, as I said that these are very important. Then we can prove easily that J and G are preserved by the flow of any vector that is tangent to F. So R holonomy invariant. So in other words, G is bundle-like because G and J were induced by G. Okay, to prove that the foliation is transversally Kähler, the difficult part was number 3, condition number 3 in the definition. So we need to show that J is parallel. This is what we want to prove. And we can split it in 2 cases. The first case is easily checkable. That the connection applied to J along any vector field tangent to F is 0. So this is 0 for any x section of L. This is okay. This is an immediate property of everything we said so far, that J and G are holonomy invariant. The slightly trickier part is to prove that this is 0 when X is a section of the orthogonal of L. So let's take X section of the orthogonal of L. Let's take a section of the conormal bundle and let's compute. We have that nabla prime applied to J along X in S is, we apply the rule. Okay, but since this is bundle-like, since G is bundle-like, we had an explicit description of who this nabla prime is. Nabla prime was the unique connection that was metric and symmetric, or torsion-free, if you want. So we have it here. Let's call this star. So it's from the previous discussion. It's exactly pi, the projection, applied to the Levi-Civita connection of G, applied to these vectors, to these vector fields. Right when this Y of S was such that it projected to S. Now we can put everything inside pi. And we know this term. This term is nabla of J of X applied to Y of S. Nabla, the Levi-Civita connection of G. Okay, J is not parallel with respect to G. Otherwise, it would be Kähler. So this term for sure is not 0. However, its projection will be 0. Why is that? So first of all, let's not even think that it's possible for J to be parallel. J is not parallel because otherwise G is Kähler, which is false. But we happen to have a fortunate equality that holds on any LCK manifold. So this equality that I will write down is valid for any LCK, not necessarily for Weissman. The true force of Weissman, or AKA of theta being parallel, was used so far. So, but the following equality holds. On any LCK manifold. It is the following. Nabla J X Y. So nabla being the Levi-Civita connection of an LCK metric is the LCK metric in X and Y times the metric dual of the Lie form plus, now the metric, not the form, times J theta sharp minus theta Y JX minus J theta Y X. Okay, how come this equality? This is just because if we write down locally that the metric is conformal to a Kähler metric, this happening locally, we write down that that J is parallel with respect to a conformal metric, because that metric will be Kähler, and we get some equality. We get some long equation from that. And then at some point, we will glue together the differentials of these conformal factors, and we get this global thing. Of course, behind it is just the fact that there is a relation between the Levi-Civita connection of a metric and the Levi-Civita connection of a conformal metric. Okay, anyway, since X was chosen to be a section of the orthogonal of L. So since both X and JX are the orthogonal of L, it means that there is no, it means that there is no part with Jx and X in this expression. So nabla of J in X and Y will be just omega xy theta sharp plus G times J theta sharp. So this further means that pi of such a thing is 0, because pi will send theta sharp and J theta sharp to 0. So therefore, F is indeed transversely Kähler. Okay, a few facts about the so-called basic cohomology and basic forms. We shall call the K form basic. So with respect to a foliation F, of course, if the interior product of eta with any vector field tangent to the foliation is 0, and the Lie derivative of eta along X is 0 again for any vector field tangent to the foliation. So let's denote by omega kb all the basic forms in degree k. We have two important remarks. It's actually only one. That the differential of a basic K form is still a basic form, of course, of degree K plus 1. And yeah, this is just because if we look, we have on one hand that the Lie derivative of eta is 0, but this Lie derivative, according to Cartan formula, is this differential plus the interior product of x of d eta with x. This was, however, 0. So it means that the interior product of d eta with x is 0. So d eta satisfies already the first condition. And the Lie derivative of d eta it's just the derivative of the interior product of the eta, interior product with x. And this is 0, because this is 0. Okay, so it's clear that actually the usual derivative, the exterior derivative, will simply descend to basic forms. So we have as a subset k basic forms. And we can take d restricted to omega kb. This will be a subcomplex. So let's call this differential restricted db. Okay, since it is a complex, it means that we have a cohomology. So the cohomology of the operator db is called the basic cohomology. Of the foliation f. Since the foliation happens to be for us, so far, whenever I started saying some fundamental things about foliation, everything applied to any foliation. But in our case, it will be very important the setting. It will be very important that this foliation is transversally Kähler. It will be crucial. So now we will develop some Hodge theory on this foliation. So the first thing is that we can define some Hodge operator. We can define, let's call it star prime. A Hodge star operator of the transversal part of G. So we can define it on basic forms with values in 2n minus 2 minus k basic forms. So, okay, this might seem strange at the beginning because the Hodge operator associated to a metric sends a k form to a n minus k form if n is the top dimension of the manifold. Well, for us, let's say n is the complex dimension, so 2n is the real dimension. But in our case, we don't have basic forms in dimension 2n, in dimension 2n minus 1, because a form of dimension 2n or 2n minus 1, degree 2n or 2n minus 1, will have a component that does not vanish on theta or j theta. So won't satisfy the first property of being basic. So basic forms go to maximum 2n minus 2. So it makes sense to consider this star prime from k to 2n minus 2 minus k, since 2n minus 2 is the top dimension of the basic form. And this star prime can be defined using the usual star for G. So star of alpha, which would be normally 2n minus k form, to be defined as j theta wedge star prime of alpha. And this is a 2n minus 2 minus k. So in total, it's a 2n minus k form. So this is how we take star prime. Having a Hodge star operator and having a differential dB, it means that out of dB, we can define an adjoint operator, delta B. And we can define a basic Laplacian by taking dB delta B plus delta B dB. So, okay, here I'm hiding under the rug some details, but the thing is that we can behave just as in the normal setting for Hodge theory, and we shall call alpha a harmonic basic form if it is harmonic with respect to this basic Laplacian. And let's take it as a fact that the basic harmonic forms will give the basic homology groups, just as we expected. I mean, this is not a surprise that things should go like this. So these are K harmonic basic forms. Okay, we defined real valued K basic forms. Of course, in this way, we can define complex valued basic forms, but we can define also PQ forms, and nothing is stopping us to take the complexification of the conormal bundle yeah, and this will split as a part of 1, 0 part and the 0, 1 part. And K basic forms, complex valued, are of type ST, is the direct sum of the forms of type ST. That are basic. So maybe I will put here maybe basic ST forms. And even the basic differential splits in this way. And we have a basic Dolbeault homology. Okay, this transversally Kähler foliation comes with a Kähler, with the so-called Kähler form of the foliation. So this is not a Kähler form on the manifold, but we shall call the Kähler form of the foliation this 2 form omega b, defined as the metric G on Q, applied to the complex structure, the J, applied to the projection of X on Q, the projection of Y. So this is for any X and Y vector fields. And this omega is a basic form and it is closed. Okay, now that we have also PQ forms, we have del bar, operator, d bar, as you probably already guessed, but I'm hiding here many details. So it's just generalizing the usual setting of Kähler manifolds and relations among operators, we have, but as a consequence of the fact that this foliation is transversally Kähler, that we have this relation between the two Laplacians. So this box operator was the Laplacian associated to the D-bar operator. Okay, so this is mimics very much the case that we know. Because on a compact Kähler manifold, when we have a genuine Kähler metric, then we have this relation between the Laplacians. So this would further imply that the K-harmonic basic forms split as a direct sum as ST harmonic basic forms. Harmonic in the sense of the bar. And we have also some analogs of the operators L and lambda. So L was the preferred letter to denote the operator that was wedging with the Kähler form. In this case, L prime of alpha means wedging with this form, Kähler form of the foliation. So with omega b. And lambda prime is the adjoint of this operator. So we'll take some ST form to an S minus 1, T minus 1. Basic form, and lambda prime of beta is the so-called interior product of beta with respect to omega b. Okay. So we have to go through this to understand more or less how Tsukada's theorem was proved. So we'll take this as a fact. It was proven by Kashiwada and Weissman that if we have lambda a K form on a Weissman manifold, so let lambda be a K form on a compact Weissman manifold, and this K is strictly less than the complex dimension of the manifold. So it's less or equal than n minus 1. Then lambda is harmonic. So harmonic with respect to the Weissman metric. If and only if lambda is alpha plus theta wedge beta, where alpha and beta are harmonic basic forms, so alpha of degree k and beta of degree k minus 1, that have the property that lambda prime of alpha is 0, lambda prime of beta is 0. This is something called effective in foliation terminology. So just a small definition that lambda prime applied on a form being 0 means that that form is effective. Okay, of course, in proving this, many relations between these operators are used, and things are quite similar to the famous relations that we have between operators on in the Kähler setting. So this draws the attention to this following space, the forms that are harmonic basic and that are effective. So let's take the K forms. That are harmonic basic and that are effective. So this fact that we shall accept for the moment tells us that the K-Betty number of the Weissman manifold, so K, don't forget that is less or equal than n-1, is the sum of the dimensions of Sk and Sk-1. So these are finite spaces. So this dimension, anyway, let's believe it for the moment. This dimension is indeed possible to consider as a number. It is anyway a consequence of elliptic theory and the compacity of the manifold. Okay, on the other hand, we can say something more, again, mimicking the case of Kähler manifolds. On the other hand, any lambda that is harmonic basic I remind you that this meant the Laplacian, the base Laplacian applied to lambda equals 0, admits this unique decomposition. So can be uniquely decomposed as the sum of from h equals to 0 to the integer part of k divided by 2 of the operator L prime composed with itself h times applied to a k minus 2h form harmonic basic and effective. This is again another little black box that we will use. So this means that the dimension of the basic homology in degree k is the sum of the dimensions of the spaces S, K minus 2H of F. This space is defined here. Okay, in particular, this tells us that the dimension of the first basic homology group is the dimension of S1. The same for H0. But we said that the Betty number in degree k was the sum of the dimension of Sk plus the dimension of Sk minus 1. So these are real. So this means that the dimension, that the first Betti number is the dimension of H1B plus 1. Okay, all this was to arrive to this equality here, because the basic homology actually can be proven to obey the same restrictions that the Betti numbers of a compact Kähler manifold satisfy. So obeys the restrictions of the Betti numbers of a Kähler compact Kähler manifold. So H1, it means it's odd. So the first Betti number, is even. So this number here is even, it's divisible by 2. So Betti 1 is odd. Right, the odd indexed Betti numbers of a compact Kähler manifolds are even. Okay, this is how we proved finally the first point of Tsukadas theorem. Of course, I hid many details, but all of them derive from many equalities, many relations that these operators, L prime, lambda prime, satisfy, and everything is mimicking the Kähler case. How about the Hodge? What about the Hodge decomposition? So for the Hodge decomposition, we have to accept another decomposition of PQ harmonic forms this time that says the following thing. So if lambda is a PQ form, then it is harmonic with respect to d bar if and only if it decomposes in this way, where lambda is of type PQ, beta is of type PQ minus 1, and alpha and beta are both harmonic basic and effective. So this further implies that PQ forms are actually given by S PQ forms that are basic, summed up with S PQ minus 1 forms that are basic. Of course, we have a restriction here that P plus Q is at most n minus 1. So a PQ form with P plus Q at most n minus 1. Okay, to be clear, what I denote by SPQB of F, I denote those forms of type PQ that are basic and that are harmonic basic. Since the Laplacian is twice the Laplacian corresponding to the bar, we can write like this. And furthermore, they are effective. Okay, due to this equality between the Laplacians, we have a splitting of the spaces of the basic, harmonic basic effective forms. So K harmonic basic effective forms split as the direct product of PQ basic harmonic forms that are effective. Okay, so out of this equality here, and this equality here, this isomorphism, so I will call it 1 and 2. So from 1 and 2, and from the fact that the K cohomology group is isomorphic to K harmonic basic effective forms summed up with K minus 1 harmonic basic effective forms, it means that for K at most n minus 1, we easily get the Hodge decomposition. P plus Q equals K. So this is just, it's obvious from relation 1 and relation 2 and 1 and 2. Okay, now we can reverse this by using Poincaré duality and Serre duality between the Hodge numbers. So using Poincaré and Serre duality, we get that this equality, the Hodge decomposition, holds also for K at least n plus 1, so greater or equal than n plus 1. So the only problem left now is in degree K equals n. But for degree K equals n, we can use the fact that we know how to compute the Euler characteristic. The Euler characteristic is given by the alternate sum of the Betti numbers on one hand, n is the complex dimension, so 2n is the real dimension of the manifold. And on the other hand is given by the alternate sum of the Hodge numbers. So therefore, the nth Betti number has to be equal to the sum of the Hodge numbers in degree PQ. And since the manifold is Weissmann, so it admits a nowhere vanishing vector field, which is the metric dual of theta, this Euler characteristic is precisely 0. Okay, so let's say that more or less we proved the Tsukadas theorem. We had indeed some black boxes, but they come for computational reasons. Okay, I think this is a beautiful result because it subscribes to the line of thinking that cohomology is somehow influenced by the metrics that the manifold can support. So throughout the course, so far we went in this direction. We presented more topological and cohomological aspects of manifolds admitting LCK metrics, focusing on Weissmann manifolds and focusing on examples. But there are many other beautiful results that subscribe to some other line of thinking. And I would like just to briefly mention them so that you see there is much more to this story. So many beautiful results are within this, this line of thinking that compact LCK manifolds satisfying some exceptional conditions. I will put it like this. Are in fact forced to be Weismann. I mean, these exceptional conditions will impose a certain rigidity to the manifold, and they are forced to be Weismann. So these exceptional conditions can be either symmetries, special symmetries that one could impose. And here I would mention the following result due to Nicolina Strati, stating that a compact toric LCK manifold, not of Kähler type, admits a Weismann metric. I mean, it is of Weismann type. The symmetry here being given by this toric assumption. I mean, in this case, toric would mean an effective holomorphic action of a torus of maximal dimension that acts in a good way, in a twisted Hamiltonian way. Other symmetry conditions that one might consider are what about homogeneous LCK manifold. And we have this theorem of Gauduchon, Moroianu, and Orna. Saying that a compact homogeneous LCK manifold is, as a matter of fact, Weismann. So again, strong symmetry assumptions will force the LCK manifold to be Weismann. Or other types of exceptional conditions could be Riemannian constraints. And here I would mention the following results due to Moroianu, and Orna, stating that a compact LCK manifold whose Lie field, or the metric dual of the Lie form, holomorphic, with holomorphic Lie vector field, is Weismann provided that either the Lie field has constant length or the metric is Gauduchon. And finally, I would mention another Riemannian constraint. So this is due to Moroianu, stating that if we are in complex dimension strictly greater than 2, so at least 3, a compact LCK manifold carrying a non-trivial parallel vector field is Weissman. Compact LCK, again, not GCK. Okay, so this would be the end of the course. I would like to thank you very much for following the course. And please do not hesitate to ask me any question. I will write here my email address. I would be very happy to take any questions, and good luck with the rest of the school, and hope to see you on some future occasion in person. Goodbye, everyone.